Welcome. My name is Paul Edison-Lahm. I'm the Communications Director and Board Past President for the Geological Society of the Oregon Country. Normally this time of year, we do a tour of downtown Buildingstone geology, and we do another one in the fall, but who knows what'll happen. We're not out there today, so this is a sort of overview of the highlights of that tour that we've been doing now for well over a decade. I used to work in this building. This is the Multnomah County Courthouse. It's a beautiful old building that's kind of being mothballed at the moment. It was controversial in its time because all of the marble that was used in the hallways and entryways and bathrooms and courtrooms as well, some beautiful examples of marble. I spent many years there working with the dedicated public servants who work in that building and spent a lot of time walking these halls, sometimes looking down at my feet and noticing interesting things in the floor, in the marbles there. These are fossils, obviously, but I was very curious about their origin and how you could have fossils in marble even. And fortunately, around that time, we met these guys, the Geological Society of the Oregon Country, which is the oldest collaboration of amateurs and professional geologists in the Pacific Northwest. They've been doing field trips and lectures since 1935. And in fact, since about mid-1950s, the Geological Society has had this downtown tour that had kind of gone moribund for a couple decades. But when we restarted it, right off the bat, we got 82 people to come on our first tour. And so we've been doing it twice a year now for almost a decade. And we always get a good crowd for that. And we'll welcome you when we start that up again, whenever we're able. Tonight, I'm just going to talk about the 10 or so basic rocks that fall into the three categories that we all know from elementary school of igneous, sedimentary, and metamorphic rocks. And that gives us about 10 basic rocks that you find as building stones. These are rocks that are sturdy enough to hold up to being used either structurally or as a veneer in a building. Starting with the igneous rocks, which are in many ways the simplest of the rock. And of those, even the simplest is what we call gabbro, or if you were buying a countertop, you might call it black granite. But it is similar to granite. It's in the same family, but it comes from ocean crust. And so it's some of the simplest of the material that you find in building stone. It has not had its chance to mix with the continents and to have more complicated silicates. And so it's just very basically these black minerals, olivine and hornblende or pyroxene perhaps, with some flecks there. You see there the shiny flecks of plagioclase feldspar. So that gives it a little bit of character. And one of the things it does very nicely is it makes a good contrast for carving. So it's used, for example, at the Vietnam Memorial in Washington, D.C. It's being used here at the Hatfield Federal Courthouse downtown. Here's another example, the beautiful garden stair by Northwest artist Larry Kirkland that is found in the Multnomah County Central Library. So it's a very common stone. It's even used in grave markers as well. Another related stone is basalt, and basalt you get when you've got a mantle plume coming up underneath the Pacific Plate, which as the Pacific Plate is dragged over the top of it, it leaves a chain of volcanoes behind. When that mantle plume erupts with very much the same material as the gabbro, you get this stuff. This is from the 2018 eruption on the Big Island of Hawaii. It's the same material as gabbro, but it gets to cool very fast. And when it does that, well, we get basalt. Here's basalt. It's the same material as the gabbro. You can see some little flecks of white plagioclase feldspar, but it's basically just a mass of gray, maybe with some little bubbles in it. That's really good for certain kinds of structural stone. And the reason that we have so much of it in the Pacific Northwest is this amazing story that many of you might know of the Columbia River basalts. The story here is that about 16 million years ago, giant fissures opened up in eastern and Oregon and Washington and filled the whole Columbia watershed with a massive flow of basalt. that followed the course of the Columbia, as you're seeing there, all the way to the Oregon coast, where it came into the sediments and came up again as undersea volcanoes, and that's what Haystack Rock is. It's an incredible story, and even more incredible that it might be tied in with the Yellowstone hotspot story, which is another story which I won't get into. But you can see there over and over again, we have these floods of, in this case, it looks blue, the floods of lava that flowed all the way to the Oregon coast. What that left behind, it might have looked like this at the Columbia Gorge, if someone had Photoshop 16 million years ago. It flowed all the way, and it left these sheets of lava that cooled very slowly. So these flows might have been tens or hundreds of feet thick. As they cool, they crack perpendicular to the cooling surface, and so you get these columns, this columnar basalt, these roughly hexagonal columns. So that makes it very easy to quarry in some ways. And some of our earliest buildings in Portland are made of structurally these chunks of basalt, these big, we're looking here at what's now the UCC church, but was the first congregational church built in the 1890s. And there the basalt, the gray rock, is being used structurally. It's actually, 3 feet thick, these blocks that were quarried out and used in a lot of churches in Portland in the 1880s and 90s. The problem with basalt is when you get to modern steel frame buildings, we're no longer using stone as structural. We're using it as a veneer, which usually means you've got maybe a 4-inch slab that you attach to the building with a metal frame. And here, this is our friend Joe Conrad of Conrad Stonecutter showing how that veneer is attached to the building using the steel frame. Well, basalt doesn't suit that very well because it tends to have too many fractures in it. So what you see nowadays is it's often used ornamentally. And here, this is in front of the federal building. You can see those columns have been quarried out, and they're being used in a decorative fashion, which tends to be how basalt shows up in people's yards and gardens these days. A third type of igneous rock comes from where you have a subduction zone. You've got that oceanic plate descending under the continent. And as it does so, at about 60 miles down, it starts to release all that water that was sitting on top of it for millions of years. That water rises as heat rises, and as it does so, it melts the rock above. And then that melted rock, you can see that those orange blobs of lava start to rise. And when they reach the surface, they erupt. And that's what our cascades are. That cascades are that oceanic plate descending, releasing water, causing the rock above it to melt, that melt moving upward and then erupting as sticky, highly silicate lava, because the lava has had a chance to pick up all the intervening material in the continent above and create more complex silicates like quartz and feldspars and micas and so forth. When it erupts into these pointy volcanoes like the Cascades, and that's what we have all the way from Canada down to California. But not all of it erupts. Some of it gets stuck in the magma chamber and solidifies there. And it may take decades or centuries for it to fully solidify. But when it does, it has time to crystallize. And that's where we get our proper granites. And here's a close-up look of that very typical granite texture or coloration. The pinks and grays and cream colors and black. And what that is it's potassium feldspar, K-spar is the pink. The cream color is the plagioclase feldspar. The black tends to be hornblende or mica, and then you've got quartz, which is the gray. Your mileage may vary. You can't go on color alone because there are going to be variations, but that's a set of colors that you're going to see over and over again. Much of our granite comes from the Sierra Nevada batholith, which is the ancient magma chamber of from back in the day when the Farallon plate was subducting under California. There was a cascade-like range, maybe 100 million years ago. Those volcanoes are long gone, but now the magma chambers have sort of popped up to be eroded. And so we get some of our beautiful granites. Some of the first granites you see in buildings, 19th century buildings in Portland, are these Sierra batholith granites. And here again to the Multnomah County Courthouse, we've got Sierra White is the brand name, and that comes from Raymond, California. You see this a lot. You see it as steps in buildings. It holds up well to wear. This is not the best view of it, but you can see there's some feldspar there in the white mass, and then rectangular hornblende crystals, and you'll see flecks of mica as you walk by if it catches the sunshine. One of the coolest things is there are hexagonal mica crystals in this. With a magnifying glass, or maybe with a good pair of eyes, you can see their little hexagonal crystals. Here's a more classic granite with the pink in it. This is at the Coin Center, and it's got crystals that must have taken, oh, I don't know, a century to develop. And this is pictured as that large yellowish cream plagiocrolase crystal surrounded by the pinks and the grays and the blacks. You can see here that the crystal has had these layers that developed over time. We call this a zoned crystal because the melt has changed, in the century that it took to, and I'm making that time up, but the melt has changed so that there's subtle variations as the crystal grows. Here's a K-spar, potassium feldspar crystal that you can see really clear divisions in the zonation. Okay, so that's our igneous. Next, sedimentary. One of the most, one of the first rocks that I learned about, sandstone, because I grew up in Southern California and it's all over there. What's distinctive about sandstone? Well, naked eye or with a glass, you can see the individual grains of sand. And you can also see bedding planes. So I don't know if you can see my mouse pointer. When you have lines that go in one direction in a sedimentary rock, it usually means that gravity is perpendicular to that direction. And so here we're seeing the original bedding planes that are kind of outlined there with a darker material, which is probably just sort of rust. It's oxidation of the iron minerals in there. But that's a typical, these are layers of sand that were laid down either in a river or a lake, or more likely a delta. Here are two 19th century buildings that use a very common use of sandstone, and we don't have the railroads coming in full force at this point. So everything has to either come in overland or more likely by boat. So in the 19th century, we're still seeing a lot of material, building stone from the Pacific Northwest. On the left is Pioneer Courthouse, and it's mostly made of Washington Tonino sandstone. To the right is the First Baptist Church, built in the 1890s. Once again, it's got that layer of basalt on the bottom where it's a higher traffic area, and then it uses the sandstone above. This is a Wilkinson sandstone, also from Washington. Those are really the only local stones that get used in building stone in the Pacific Northwest. The Tonino is what stonemasons call a freestone. It doesn't have clear bedding planes, so it's easy to work. And so we see in the late 19th century, a lot of this carving is done in Tonino. There's just some beautiful carving at the Imperial Hotel from 1894, looking at the Deacon building, which is this wonderful, magnificent Richardson Romanesque building. And it's got, in addition to those columns that are carved, it's got wonderful details like this green man that are carved in that Tonino, that Washington Tonino freestone that holds up quite well after 100 years. But it fell out of favor, and for a number of reasons. Here's a letter from the Tenino Commercial Club in about 1910, written to Reed College, which was building its college at that point. And the letter implores people to not start using this interloper limestone that was starting to become very popular. Unfortunately, the local stone kind of fell out of favor. It doesn't hold up quite as well, and it lost out. Here's what Reed went with. Reed went with East Coast, or rather Midwestern Indiana limestone, which is very popular in civic buildings all around the country. That takes us into a new area of rock type. We've been looking so far only at silicate rocks, rocks that have the building blocks of the sort of silicate tetrahedron and make up the minerals of olivine and hornblende and feldspar and quartz. But our carbonate rocks come from calcium carbonate, which has its origins in tropical seas. So it's the calcium carbonate that precipitates out in tropical seas or is used by creatures to build their shells. And that's where we get our limestones, and eventually we'll see metamorphose into marble. So starting with limestones, also I've put a fossil there for reasons you'll see. Fossils you really only find in limestones and sandstones, and really in Portland you only see them in limestones. So we'll talk about that in a moment. Here is this is that Salem limestone I mentioned. This is at again, the Hatfield Courthouse. I walked by this for years thinking, oh, that's artificial, that's man-made. In fact, the blocks have been carved out with a pneumatic hammer, probably. So they do look kind of uniform, but on closer inspection, they're fascinatingly complex. They're just full of stuff. Either with a sharp pair of eyes or a magnifying glass, you can see lots of little critters. They're that Chex Mix-like creature is a bryozoa. It's an animal common to tropical seas. Or you might see a foram. These are shell-like creatures that can be millimeters across and that are somehow single cellular, which kind of blows my mind. Also, you'll see these little ooids. These are grains that got rolled around on that tropical sea in the warm, and just imagining the warm water, rolling these things into little balls. And so you get this wonderful ooidal or egg-like shapes in the stone. Limestones around town are one of the best places to find fossils. And here's the fountain at Pioneer Mall, and it has wonderful fossils in it. You see that sort of reddish color of I'm not sure if you can see my mouse, but this is a turritella shell or cone shell. This is a gastropod or snail. And here we've got on the right, the star-shaped crinoids, which are sea lilies, the sort of, well, they're related to starfish, as you can tell. That has this five-pointed structure underneath. So those crinoids are the stems of those sea lilies that are found in this case, it's a dark black Jurassic age limestone. Go to the coin building and look at the sides. We see animal tracks in the limestone there. We see barnacles. We see even sea urchins right there at Street View along in the limestones at the coin center. Travertine is also a carbonate-based rock, and it comes from mineral hot springs, such as Yellowstone here. It has a very interesting sedimentary texture. Again, we can see the bedding planes are running one direction. That means gravity is running perpendicular. There's a lot more structure to this, though, than we saw in the sandstone, and that's because well, I'm not quite sure why. It's the way that the hot springs work, but maybe there's even some influence of a thermophilic bacteria in there that's creating some of the voids and the structures in the stone. You see it used in classical settings often. This is Pietro Beluschi's Portland Art Museum in a modernist idiom, but it's still got classical elements to it. And so the travertine is suggesting that connection to Greece and Rome. And here's here's a version of it, Italian travertine in front of the Justice Center that needs to be cleaned up. All right, now we move into our metamorphic rocks, and the stories get more complicated here, and I think in some ways a little more beautiful because you get to see some really pretty minerals popping out. We're going to start with serpentinite, which has one of the most complex stories. It looks like marble. You might call it marble if you bought it in the store, but it's nothing like marble. It's closer to an igneous rock. You see it a lot as sort of semi-ornamental. Here it is being used as a street level rock, which maybe not such a good idea because it does tend to erode a little bit. It's pretty soft. Its origins are ocean crust that's picked up some carbonate minerals and it's gotten subducted and metamorphosed under heat and pressure. It is the state rock of California, so it's all over Northern California especially. It's a beautiful material. And it looks like marble because it is sort of marbled, but it has an igneous origin. That's a close-up view of it. What does the green come from? I want to say chlorite. Okay, moving along in our metamorphic rocks, what happens when you have a sedimentary rock and you metamorphose that under heat and pressure? Well, slate is a very common example. So slate might have started off as a shale or even as a marl, as a volcanic rock, but it's been metamorphosed to the point that it has planes that can be fractured easily and used as a pool table perhaps, or here at Reed College, you see this Vermont slate being used as shingles. Here's another building that has a marvelous use of slate. I didn't used to like this building very much. It's the Union Bank building. It's kind of offset from the street, a little bit formal, and the cream-colored pieces of it are just colored concrete. So I didn't really like it very much. But then I noticed this beautiful, or had pointed out to me, this beautiful slate that's actually, it's a volcanic marl, which means that it once was a volcanic eruption that fell into water and settled there. So these layers are bands of, volcanic ash that have settled in the water and solidified into a slate over time. They have some fascinating structures in there. There's something called flame structures, which are little spurts of water, I guess, or spurts of as the whole mass becomes compressed. So it's worth taking a close-up look because the rock is fascinatingly varied. As you even in this big modern building, it's got the very rock that has a lot of character and a beautiful color to it. Okay, we're moving on to gneiss. Everyone's entitled to at least one geologic pun, so you can make it at this point or save it for later. Gneiss it's either a sedimentary rock or an igneous rock that's been further metamorphosed to the point where you get this kind of foliation. What happens when you apply stress to a rock over time is that especially the darker minerals will reorient the olivine and the hornblende and so forth. And so you get lines that are perpendicular to the lines of stress. So unlike a sedimentary rock where you get bedding planes that are perpendicular to gravity, here you get these foliations that are perpendicular to the stress on the rock and tell a story about what that rock has been through. This was probably a granite. You can see kind of the same colors of, the pinks and blacks of that we saw in the granites earlier, but it's been through a lot. And so as a result of stress that you see there with the arrows, the black minerals have, the hornblendes and pyroxenes and so forth have kind of gotten together, and the feldspars have gotten together, and they're forming their own bands. And so you get this wonderful foliation. Take that still further, add a few billion years, and you can get some really fantastic stuff. This is the Morton gneiss. over in the Carl Grieve building across from Nordstrom. The Morton gneiss, which is 3.6 billion years old. And it's just fantastic. It's psychedelic. It's got at least 2 layers of story. The gray older rock is the 3.6 billion years old. And then that pink tonalite was injected about 2.5 billion years ago. And this rock has just been through hell, but it's a beautiful result. And it's got a fascinating, wild texture that, again, it's just marvelous to me that you can walk down the street and see something that is, well, basically a quarter the age of the universe. That's a close-up. Yeah, look at that stuff. All right, our last rock type takes us back into the carbonate rocks, and that is marble. How do you get marble? Well, you take limestone or travertine and you stick it under a mountain, and under heat and pressure, minerals move around and create a metamorphic rock. I just made it sound very boring. It's anything but boring. This is Italian marble that's got a little bit of organic material maybe left over that leaves those gray marks. Here is a purer version without the organic material from Greece. It's I think it's the same marble that was used for the Parthenon, if I recall. Here in the statue, the Quest, which some people know as 3 groins in a fountain in front of one of the standard insurance buildings there. Here's another version of it at the Wells Fargo Tower, which incidentally was built by an architect who had worked on NASA buildings. So it's got a sort of space age feel to it. It's another building I didn't really think much of, partly because I just thought it as a big concrete monolith. But in fact, the entire building is sheathed in Carrara marble, the same marble that Michelangelo used. And that's made me appreciate it a little bit more, partly because it picks up light in a nice way, depending upon time of day. And it does suggest a little bit more of the kind of classical monumental structure that the people who were building this bank were trying to go for. Marbles are fascinating, and I think geologists tend to look for a simple story in the rocks we're looking at, and we're looking at the sort of overall tectonic story maybe. But marbles tell a much more detailed story of, the original deposition of the carbonate minerals, and then maybe, they were in a cave, and the cave had a cave in, and there were fossils in the cave, and then there's other alteration of minerals that result in different colors. I couldn't tell you what's going on with this one, but something is, and it's quite fascinating. I suspect that each marble has its own sort of unique story. Going back to the Multnomah Courthouse, there's some really beautiful examples there of just there's a much more complicated story here that results in those fractures, that coloration, and so much variety. This is a beautiful red marble in one of the courtrooms. This was a few years ago when OPB was doing an Oregon Field Guide taping. And these were the fossils that originally caught my eye in staring at them in the tile floors of the bathroom of the courthouse. And I was fascinated because I saw that there were sort of these fragmentary pieces that suggested sort of brecciation or broken up rock. But then there were these round things, and I couldn't figure out, well, how can you have a round thing in a metamorphic rock? Turns out those round things are coral. Boy, the term is escaping me. I want to say rosette, that's not it. Rugosa coral, and they're an indicator fossil. The fact that we're seeing them there means that this happened before the Permian extinction, and those are Paleozoic. Those are really old fossils. In fact, they're Mississippian age. They're about 325 million years old. Well, how can you have a fossil in a metamorphic rock? Wouldn't the metamorphism destroy the fossil? That's usually true. In this case, though, what we're really seeing, though it's called a marble, is actually still a limestone. It hasn't really fully metamorphosed, and so you can still find fossils in limestones. So that's a word to the wise. If you are seeing marbles, it's always worth looking to see if you can find a little fossil somewhere. All right. Well, these are the activities that our club normally engages in. We have monthly lectures, monthly meetups, trips that are local, that are just a couple hours long, and overnight trips to Eastern Washington and Oregon and the coast. Special events like picnics and banquets. All of that is totally up in the air right now. But we will have them. These are field trips that we had planned for 2020, that many of which will just roll over to 2021. Rafting trips and helicopter trips and hiking trips and even a bike trip. Our downtown trips we usually have twice a year. We won't have one this June. We probably will go ahead, hopefully in October with our North Tour, and we might want to schedule another one. And we'd be happy to schedule one that was sort of specific for any of our sister clubs who have common interests with us. All right, well, thanks. You can find more information about our organization and whether our lectures are going to, or our events are going to be online or in person at gsoc.org. And thank you very much.